Yes, we can.
So let's continue our lectures, and today we will see some generalization of the previous results from several points of view. So let me recall what have been done on the previous lectures and what we will consider today. So I want to recall you that we proved so-called Campbell formula that show us how we can find the expectation of integral with respect to point process. So this formula was for any point process. With intensity measure lambda. We proved that we want to find the expectation of integral of some function with respect to point process eta. Then this is equal just integral of function f of x with respect to intensity measure. So this was proved, and it was not so hard to see just from the definition of intensity measure. But today we will produce more general formula of such type. And what is the idea? So now here we can see that a function that we considered was dependent only on one point. But in many cases, later we will see the necessity to consider functions that depends not only of a point, but of all point process also. So let us say that what if we consider a function f that depends on a point x and on a measure? So what it is, so here f now acts from the space where we consider our points, and it depends on whole measure. So this a function from such a product where here x is the space of a point and n is the space of measures, and it's x to r, for example. Let us see some examples of what can be such a function. Example. So next we will see that it is arise such question about following problem. So if I want to investigate a point process, so we remember that this is a collection of random points. We can consider this in such way. And now the question is the following. If I observe some point x at some specific region, and what I can say about the distribution of another point. So this is some sort of a prediction based on partial information. So if I know that some point located here, and what I can say about the distribution of other points. So this leads to investigation of the following functions. So they will depend on a point and on a measure itself. So for example, I want to say that I observe a point x at some subset delta, and my question is how many points I will find in neighborhood of this set. So, for example, I say that mu of ball is equal to k, for example. So this will be delta on my picture, and this will be some subset. So this is natural question that arise in the theory of a point process. So the question is, what can we predict just based on some information on some point? So this is example of a function that can be considered of such form. Of course, we can produce a lot of different examples. For example, another one, if I want to find, assume that I have point measure mu of the following form. This will be some, this will be delta measures at some points xi, I from 1 to m, and I can ask what is, for example, the distance, the average distance from fixed point x to this point xi. So this is also a practical problem if we have some fixed point and here random points of the measures of the measure mu. So we just measure the average distance to points of random measure. And so on. We will see later some application what we can consider here. And of course, now when we consider such examples, and if we come back to the Campbell formula of such type, now I will write not only the function that depends on a point and measure, but I will consider such integral with respect to this point process itself. So let's now consider such for a function that depends on a point and a measure. I will write the integral of such form where I integrate with this measure itself. So what is it if I have a point process of the form here? We already discussed that such an integral we just can consider as a summation with respect to these points x. This will be just summation here with respect to all space where we consider our point process xi. So what is this object? So if we come back to our examples and I want to know if I have a function of such form x eta is equal to indicator that point x belongs to some set delta and number of points in B is equal to k, for example. This is delta and this is. So now when I consider this integral, I will sum over all points of my point process of random process of points here. So I will consider such, so I will have here 1 only in that case if a point process have a point, at least one point in this subset delta. So later we will see that from this point of view we can consider conditional distribution. So we will assume that there is a point in some small subset delta, and what we can say about other random points around this subset. So this is again the problem about prediction of a distribution of a point process based on a partial information about a point in some subset delta. So let us write, if I have such example, then integral x eta dx eta dx is just I can write this indicator outside of summation because it does not depend on our point. And here I write just indicator that xi belongs to theta. So, and the summation, it's not hard to see, it counts just the number of points in this subset delta. So we just get this function. This is just eta of subset delta. So this is the number of points in subset delta. So such function can say us that we can find some number of points in fixed set delta, and what we can say about the distribution in the neighborhood of this set, and so on. And today we will consider how we can find the expectation of such functionals, but today only for a Poisson point process, because for general case this is interesting but rather difficult question, and the answer depends on the structure of a point process. And the main property of a point of a Poisson point process that allows to find out how we can calculate this expectation is the that the number of points in non-intersected subsets is independent. So this is the main property of the Poisson process that we will use today. So I will announce the question now. The question is how we can find the expectation of functionals of the following form. So previously I just gave motivation for such objects, and we will see how we can find it. And moreover, we will see that the answer will characterize, so we will get the answer for a Poisson point process, and this answer will characterize a Poisson process itself. What does it mean? It means that if you have such equality for each function f, then you have a deal with a Poisson point process. And this, so we will have answer for a Poisson Poisson point process. We will have so-called Mecke equation, and moreover, we will see that this equation true if and only if eta is a Poisson point process. And with this type of criteria, I want to recall you the property of a Poisson distribution that we considered on the first lecture. We will get answer. So this is was the first recalling of a Campbell formula and how we will generalize it. And now this sort of criteria can be considered as a generalization of a property of a Poisson distribution itself. So I just recall from the first lecture, we saw the following criteria for Poisson distribution. So if I have a random variable with Poisson distribution with parameter gamma, then for every function f that acts from integers to non-negative values, we will have that the expectation of x function of x is equal to gamma, this parameter, and here we just add one value to random variable x. And moreover, we have this equation only if x has a distribution of a Poisson. X has a Poisson distribution. So if, so this is first and second, that if I know that x is random variable with values in 0, then and we have this property, and we know that for all functions this property holds, and then x has a Poisson distribution. X is a Poisson distribution with parameter gamma. So here we can see some, we will see that this is a generalization of this. This Mecke equation is a generalization of this property. So let us start to formulate the main result for today's lecture, and This is the following theorem, so-called Mecke equation. So we start from lambda. It will be as finite. I recall as finite measure means that this is at most countable sum of finite measures. And finite we understand as it is a sum of finite number of delta measures at some point. Finite measure on x, and eta some point process is a point process. So we consider some measure and point process. Now the Mecke equation says that then eta is a Poisson point process with this intensity measure. Lambda, if and only if so this is most interesting, if and only if we have that the expectation of integral of this form. So we have integration of a function that depends on a point and on a point process itself, and we integrate over point process is equal to what? Let us recall what did we have for a Campbell equation. So we had here something like this, just lambda dx. We had the integral with respect to intensity measure, but now we have here the randomness that are in a function f. So we will write the expectation under the integral of a function f, and here we need to add a point x to this point process. So I add delta measured point x at point process eta. So how we can understand if and only if we have this equality for, I will write for all f that x from x times n, and this is with non-negative values. So how we can understand this right hand side? So first we need to calculate the expectation of a function with respect to this point process, but we additionally add to this point so assume this was eta, but we add here a point x additional, and we calculate this expectation of a function that depends on x, and all this measure plus this point. So this is how we can understand it, and then we integrate with respect to intensity measure. So let us try to prove, because now we have quite long explanation and motivation for this result. So for the proof, let us start from the other side. Okay, assume that we have a Poisson process. Let eta be a Poisson point process with intensity measure lambda. And we want to understand how we can calculate this expectation. So we take a function f of such form, and let us recall how we can represent a Poisson process. On the previous lecture, we gave a construction of a Poisson process, and it was done in several steps. So I recall that we can consider at first the finite measure lambda. So assume that if lambda is finite, then we construct a Poisson process as a following. We can represent lambda in term of gamma times q, where gamma some number and q is a probability distribution on x. And we get a Poisson process eta of the form. This was the sum of delta measures at random points xi, and the number of random points is from 0 to random number kappa. So I recall kappa has a Poisson distribution with parameter gamma, and xi IID with distribution q, and moreover these random variables are independent. So we show that a Poisson process can be represented in a such way. So let us substitute this representation into the formula of this form. So we have f of x eta t x of x. So what is it? This is a summation over 0 to this random number kappa. Here we have xi, and I will write the measure eta as sum of delta measures at points x1 and so on x with index or kappa here. Now, if I write down the expectation before this expression, and what is the main property here, that we have independence here. So I will use this independence, and I can write then this expectation over all possible values of random variable kappa. So I write this summation over. And please note that if kappa is equal to 0, then we have 0 number of summands. Right. And so we have just consider the summation from 1 to infinity. So this is all possible values of kappa here. Just a moment. I from 1, of course. So I have that I consider here summation from here k, all possible values of kappa, then from 1 to k, and I write the same xi tilde x1 plus and so on tilde xk. Now I will write because I assume that kappa is equal to k. Indicate that kappa is equal to k. Okay, so now I use independency, and I can just write that expectation of this is equal to expectation of a such sum times probability that kappa is equal to k. So I just write it in this way. So the probability that kappa is equal to k, we know that this is a Poisson distributed random variable. So I have that this is the distribution of kappa. And here I write the expectation of this sum I from 1 to k. And here f of xi tilde x1 plus and so on plus tilde xk. So we have this point, this expectation. Now let us observe that. Let us separately observe this expectation. Not this one. At first I will put expectation under the summation, and I consider this expectation of function. I will take I tilde x1 plus tilde xk. So what we should observe here is that xi independent with other points. So I can write this expectation just with respect to xi. And I know that the distribution of xi is equal to q. So I will write it in form of the integral. And I just write in such form. And well, here I have independent identically distributed random variables, so I can rearrange the numeration, and the measure will not change after it. So I will write on the first place y, and then k minus 1 points x. Okay, I will renumerate them from x1 to xk minus 1. And this is integral with respect to the q distribution of random variable x. Okay, so this, and note that this is true for all I. So for all I have this form. So now I can continue.
May I ask a question?
Yeah, sure.
So on the left-hand side, we have an expectation, which is a real number, but the thing on the right-hand side looks like a random variable.
I'm sorry, I forgot to write the expectation. Thank you so much.
Okay.
This is, of course, I take the expectation with respect to xi, and then expectation with respect to other random variables. So maybe this is an analog of the following formula. If I have two independent random variables, then how I can find the expectation of some function phi of pair. Of course, I can write it in terms of integral, and I know that the distribution of a pair is the product of distributions. So I can write, for example, this will be expectation of integral, and I can write the expectation of with respect to xi, and so this is just the notation, and here's the distribution of x. This is it. So I use this formula. Okay, so I come back to this one, to this formula. To this formula. So I have exactly k same summand. So I have k integrals of expectations. So I will write them e to the power minus gamma k from 1 to infinity, gamma to the power k factorial, and now I have just k times this integral, expectation f of y delta y plus x1 delta x k minus 1 distribution of dy. And now we can see here, let me write it, e to the minus gamma, and here I will write gamma here and k from 1 to infinity, gamma k minus 1 over k minus 1 factorial. And here, again, I write expectation. 1 delta x k minus 1 q. Now let us recognize here I can write this integral just outside of all this expression, and we can see that this is just the just a moment. Gamma, right? And now here, this is what we did on our first step. We consider all possible values of summands with such distribution, with a Poisson distribution of number of summands. Yes, so we did this on the first place. Now I can rearrange it and write as follows. So this will be the integral with respect to x, and here I write f of y delta y, and this is just by the definition, this is Poisson process with that from what we started. So this is it. So you can consider what we did from the first step. Yes, we represent this function as such a summation where we consider this all possible values of number of points. So here we did the step in opposite direction. And here, what is the integral with respect to gamma? I have this extra gamma. So I write it here gamma q dy, and this is what was our measure lambda. Lambda was equal to gamma times q. So the last step, this is integral of expectation f from y dy plus initial point process with respect to lambda dy. So this is the idea. So once more, how we add this point y to our Poisson point process, we just separate, we just use this formula when we calculate the expectation. This is just because we have independent points here. Xi's are independent, so we can this step. So this is the proof of the one part. So this is exactly right hand side of the equation that we stated in the theorem. Now let us prove opposite statement that says, okay, assume that we have this equation for all functions f, and we should understand that we have to deal with a Poisson point process. So assume that for all functions f from x times measures to r plus, we have that expectation of such integrals eta dx is equal to expectation f x eta plus dx delta x, and we integrate with respect to measure lambda. Okay, so to see that indeed eta is Poisson point process, we will prove that it has independent values on disjoint subsets, and it has a Poisson distribution of number of points in any set. So to this aim, we will take specific functions f. So consider specific functions f of the following form. So first we fix disjoint subsets b1, b2, bm, disjoint subsets of sigma field on x, and bi intercept dot is m. And assume that our measure lambda on each subset is less than infinity. Okay, and we will consider the points numbers, and numbers k1, k2, and so on, km with the integers or 0. Now we define this specific function f that depends on points x and measure eta. Okay. So I will find it as follows. So it says that at subset B1 I observe point x, and at each subsets from I1 to M we have exactly k points, ki points in this subset. So, for example, on the real line, if we consider random process, so this is B1, for example, B2, B3. So I assume that I consider a point x in B1, and I have a specific number of points in each subset. So here K1, here K2, here K3. Now, for such function, let us consider what is the equation says. So we know that expectation, consider this 1 eta dx. How it looks like. So I just substitute this form of a function, and we can see that this is just summation over I will not write. So this product does not depend on x, so I put it outside of the integral, so it remains unchanged, ki, and the integral overset b1 of eta dx. So this is just equal to eta of b1. Right? Eta of b1. And if we multiply eta of b1 by this indicator, we will have non-zero value only if eta of by is equal to k1. Right? So let's write it. So eta of b1 indicator that eta of b1 is equal to k1 is just equal to k1 or 0, k1 or 0. So I can continue. 0 does not involve on the expectation, so I will write k1 times probability that we have here intersection I from 1 to m, and here eta of bi is equal to ki. So this is just by the definition of expectation. So this was the left-hand side of our equation. Left-hand side. Now let us consider how right-hand side looks like. And to this aim, right. First, we consider the expectation. In the right-hand side, we have this. Under the integral, we have expectation of x eta plus delta x. This one. This not all right-hand side, but part of it. So let us calculated for our choice of function f. So we have this product of indicators. So I write it. Let me rewrite. I have indicators that we have a point x. So this is non-random factor. I will later write it outside of the expectation, and here new plus delta x. Yes, now I have this new measure, so I substitute it as argument at my function. That bi is equal to ki. I from 1 to k, to m. So as I say, this was non-random. I write the expectation outside. And here, please know that, let me show once more the bigger picture. So we have a non-intersected subsets P3, and now we have this indicator, so we know that we add a point x only at first subset here. Yes, so this eta plus delta x will change its value only at subset B1, but at subset B2, B3, and so on, eta plus delta x just equal to eta itself. And since I know that x belongs to B1, because we consider only such events, then here I continue. Here I will have the event that eta of B1 is equal to K1 minus 1. Why is it so? Because I just drop this delta x. I do not consider it. So in B1 remains K minus 1. But at other subsets in delta 2, the addition of point x does not involve on value of the measure. So this is equal to K2. Okay, I hope I explained in details. So I have not changed values Km. So once more, for value of B1, I delete a point x and I increase by 1 the number of points. So this is the expectation, and now when I consider the integration of this one, so I integrate with respect to x. So this representation now, in this probability, I have no dependence of x. So I can just change it here. The integral with respect to lambda dx. And here I continue integral with respect to lambda dx. So only what we have, this integral with respect to lambda dx. So as you see, we have lambda of B1, and here this probability eta of B1 is equal to K1 minus 1, eta of B2 is equal to K2, and so on. So on, eta of Bm is equal to Km. Now, here we can see on my screen left-hand side and right-hand side. So we can compare them. We can compare them. And in order to, so left-hand side is equal to right-hand side. What do we have here? K1 probability that of the BI is equal to KI, and this is equal to lambda of B1. Here probability, the first set is different from other, but other K from 2 to M, eta of BI is equal to KI. Okay, so now if we consider only one subset BI, then here you can recognize the formula that I wrote on the beginning of the lecture about this characterization. So we maybe not this, but when we proved it, we use the equation for probabilities of Poisson random variable. Let me recall you how we proved it, just for recalling. So when we proved this is not about this. So for Poisson distribution, we saw that such that this equation is a characteristic equation. Gamma probability x is equal to k minus 1. So we have if and only if we have this characterization. So you just can repeat this recurrence equation, and you will see that only the unique distribution that you can get here is Poisson distribution. So the same we want to get here, but here we have additional values on subsets. So let us consider I will divide by this probability, and I will have the equation for conditional probability. So let us write not by this. I will divide. Okay, let me write. So let us denote PK. This will be conditional probability that eta of B1 is equal to K under condition that all others eta of BI equal to KI. So now if I divide by the probability of this event of condition, then I will have from this one, with this notation, I will have that K times PK is equal to lambda of B1 PK minus 1. So please note that this equation will give us this distribution that I have in brackets. So conditional distribution of number of points in subset B1 the conditional probability of V1 equal to K under this condition, Ki is a Poisson distribution, so I can write this as E minus this is parameter lambda of B1, lambda of B1 to the power K factorial. And please note, it does not depend on these values. Do not depend. It does not depend on K2, K3, and so on, Kn. So this distribution, so the next step, you just sum over all possible values of K's, and you get just the distribution of one value. Distribution of 1 is equal to K. Or I can just say this in short form, that this is a Poisson distribution with parameter lambda of B1. And since the conditional distribution does not depend on all possible values of number of points in subset B2, B3, and so on, Bk, we also make the conclusion that this random variable independent with other I from 2 to n. So we get the distribution and independency of one subset B1 with others B2 and Bn. So we just separated this one. So we can just change the function f. So here was the function f with B1 here. You can change the index of subset I. You will have the same statement for next set, and so on. So you just repeat this procedure, and we proved that our point process at first has Poisson distribution of number of points in each subset, and moreover, if subsets are disjoint, then the values are independent. And this is the definition of a Poisson process. So by the definition, eta is a Poisson process. Okay, so we proved this statement, and this is all proof for our theorem today. So once more, what we did, we can consider this statement from two sides. At first, we produced the formula how we can calculate expectation of such functionals, but only for a Poisson point processes. And we saw that here independency of points in process eta is crucial. And moreover, we get the factorization of a Poisson process. If you can prove for some point process such equality, then this proves that your point process is a Poisson point. I'm not sure that this is the best way to prove that you have deal with a Poisson point process, but nevertheless, this is such a criteria. So that's all for today's lecture, and if you have some question, you can ask.